Welcome to this video on solving constraint optimization problems numerically. In this video we will talk about how to use scipy.optimize to solve optimization problems where there are constraints that can be inequality constraints or equality constraints. We will first focus on a case where we specify these constraints and we use a solver that can sort of handle that. And then we will consider an example that's more economic where we will just add some penalty terms in our problems and then use an otherwise standard solver to solve the problem. I'm importing NumPy and standard plotting stuff, and then I'm importing the simple namespace and a way to both time and copy stuff, and finally I'm importing the scipy optimize thing. So if we consider sort of a general constraint minimization problem, we can sort of think of that we have four variables, x1 to 4, and there is some objective that we want to minimize. And then there are the constraints that if you multiply all the variables together, they should be equal to or larger than 25. If you square them and add them together, they should be exactly equal to 40, and individually they should each be bounded between 1 and 5. So if you want to specify this problem and solve it numerically, we as normally specify the objective function. But now we also specify a function that evaluates the inequality constraint. And we do that by saying, let's actually put everything on the left-hand side and see whether this is positive or negative. And here sort of the norm is that if something is positive, then it's okay. And if it's negative, then the constraint is violated. The same thing goes on for the equality constraint, where we say that this should be an exact 0 to be fulfilled. So let's evaluate this, and with these functions in hand, we can now use the optimizer called SLSQP. There are other kinds of optimizers that can take care of constraints, but this is the one I will show you. To use this, we finally need to specify some bounds. So a bound that's between 1 and 5. So that's a tuple of the minimum and the maximum value. And then all the bounds, that's just a tuple with the bound for each variable, which is here exactly the same thing. Then we specify the inequality constraint by using a dictionary where we say the type is an inequality constraint and the function representing the constraint is this in EQ underscore constraint function that I defined above. And similarly with the equality constraint. Then I make an initial guess, and when I call my optimizer, I normally, as normal, specify the objective, the initial value, the method, and now I also specify the bounds. And I specify constraints. This is just a list of the dictionaries that I created up here. And finally, I say that I want to see the results. So if I evaluate this, we can see that it finds a minimum and it returns what the minimizing argument is. So this is generally how that can be done. You might want to manually check the constraints. So here I'm printing what is actually the value of the inequality constraint if I evaluated in the result that I get out, and you can see I actually get a slightly negative number, even though we required it to be positive. But what it actually checks is that it checks whether the result of the evaluation is close to 0, then that's okay, or if it's larger than or equal to 0, then it's also okay. And this is just a very small number, so it's 0 for all practical purposes. The same thing goes on for the equality constraint. It's not an exact 0 we get out, but we get an approximate 0 out. So that's how you handle these constraints typically. Okay, so this is sort of the approach you should take if you have a general minimization problem with some complicated non-linear constraint. Use this SLSQP optimizer. Okay, but now let's look at an economic example. So we might consider a consumption saving problem that looks like this. Here the idea is that you wake up with some assets, a 0 from the last period, and then in each period you get some income, you get a return on these assets. So your cash in hand is 1 plus the return times this asset you had in the last period plus some income, and then you can consume your cash in hand, and you will have some asset in the next period, and that will then sort of continue going forwards. Consumption always has to be positive, and so does assets. You cannot borrow. You get utility from consumption in each period. You discount future utility with beta, and in the final period you also get utility from holding assets, which can be interpreted as a utility of giving a bequest. So the new and the kappa are sort of extra parameters in this utility function determining the strength and how much of a luxury it is, how much sort of bequest you get for free in some sense. What makes this problem complicated to solve is actually the last inequality constraint down here. If this was not there, then we could solve this with a Lagrangian approach, but we have these multiple constraints down here, which are inequality constraints, so that makes it a much harder problem to solve. So that's why we attack it numerically. There's a bit more details of what the variables are here if you want to look at that. You can, however, for this problem, derive first order conditions. But that they only hold if you are actually a positive saver. So if you save in either period, then we know that these conditions should be fulfilled. I don't want to derive these mathematically here, but we can sort of use them to check whether the solution that comes out actually seems to be an okay solution. You can simply just sort of use a variational argument to get these things out. But if you don't care too much about that, just take this as a sideshow. If you want to solve a problem like this, then there are generally sort of 4 steps you need to do. You need to set up parameters, you need to formulate the objective, and you need to determine how to handle the constraints, and you need to call an optimizer. So let us first set up the parameters. I just choose some values for the initial assets, and I choose some values for the preferences, the return, and so on. We have 3 periods, so I set a capital T equal to 3, and I say that normally I have an income of 1, but in the first period I actually have an income of 0. Then, to evaluate my objective function, I say that I choose my consumption and I have some parameters, and then there will be a penalty factor which I will come back to later. I create some arrays for holding how many assets and how much cash in hand and how much bounded consumption I have. I will define that below. And then I will say, okay, to begin with, I have no penalty. But then I loop through my periods. Each time I found my lagged assets, either as the assets in the last period or this initial assets that I set. Then I calculate my cash in hand, and then I bound my consumption. And I say that if my consumption is lower than some small number, then it's too low, and I set my bounded consumption equal to this, and I calculate what is the difference to this required bound. And here I take sort of the difference and I multiply in this penalty factor and increment the penalty with this. So sort of I say this is a bad thing. I do the same thing if consumption is larger than cash in hand. I cannot do that because then I would be boring. I would have negative assets. That's not allowed in this model. Otherwise, it's just fine, and I set bounded consumption equal to consumption. I calculate my end of period assets at the end, and once I'm through this loop up here, then I'm ready to calculate utility. So utility is calculated starting from 0. I add up utility from consumption. I discount with my beta each time, and at the end I add this utility from bequests, and I return my total utility, the penalty, and the vectors of cash in hand and savings choices. So this is a maximization problem. So this is sort of the utility that I get out. I want to use an optimizer, which is actually a minimizer. So therefore, I also define an objective function which takes the same inputs, but then evaluate the function and returns minus the utility plus the penalty. So the minus, that means that we turn the minimization problem into a maximization problem, and the penalty sort of says that anything that's violating this, you shouldn't go there. You should try to set the penalty to 0, and we want a penalty at 0 at the end. Okay, so now if I want to solve the model, I just say I want to make an initial guess. I set some equal consumption that's a low value, and then I call my solver on the objective with the initial guess here, and I put in the parameters as extra arguments. I use the Nelder-Mead, and I set some options for that. If it's not a success, then I raise a value error and print what has gone wrong. Otherwise, I print that I've solved the model and how long it took and how many iterations and so on. I also have an extra function that sort of creates additional results. But let's just skip over that and see what it prints out. Let's put these into memory here, and let us then sort of solve the model here. And we can see that it solved it rather quickly. It takes a significant amount of iterations, but it finds out that, okay, we have these initial assets. In the first period I have 0 income, but then I have 1 income. And you can see how the cash in hand develops, how consumption develops, and how the cash in hand, how the savings develop. You can see initially I'm constrained. I am choosing exactly 0 savings, but otherwise I choose positive savings. That also implies that the first order condition errors are 0 in the second and in period 2 and 3, but not in period 1. You can see you get some negative utility. That's just because of the utility function I've chosen, but logically the penalty is 0, so I'm not breaking any constraints here. Okay, this is a good time to pause the video and ensure that you actually understand the code cells above that produced this result. Okay, once you have done that, I think you should actually try to extend the result a bit. So before we had 3 periods, but now let's try to do this with 4 periods instead. Well, it's still the case that the first income is 0, but then I want, and this is wrong, but then I want all other incomes to be a 1. So at least try to think about how you would do that. Okay, so here I'm actually using my deep copy that I have imported. So what I will do is I would say let's make a long model here, which I will make a deep copy of my parameters. Then I will say that now I want to increase my number of periods to 4, and that also means that I should now say that my income here should be a bit longer, and I still want the first period to be a 0 income. And then I want to solve this new model here. Let's see. I succeed in solving it. That looks fine. You can see that it takes even more iterations here, and you're still constrained in the first period, and it seems okay. These errors here are getting larger, but it seems reasonable, and especially we have a penalty of 0. Okay, we could think about what happens if we begin to increase t here. So let's actually do this manually. I could put in 5. That would still work. You can see that now it begins to get some large errors here. You can also see that the number of iterations I need increase a lot. So if we begin to go up here, let's just take a crazy number. Now it begins to take a lot of time. It actually finds something, but I'm given that these errors here begins to be very large. I'm unsure about whether this is actually a global minimum that it has found, or whether it's just somewhere it ended up. That would sort of need a multi-start approach to try to investigate that, but let us not do that here. But the problems if you increase capital T is basically that now the dimension of your problem increases, and that gets harder and harder to solve. It takes a longer time, and it becomes harder and harder to actually ensure that you have found the global optimum, because it becomes so complicated. So what we could do here is we solve an intertemporal problem as if it was a static problem, because there's no risk, and therefore we can do that. But for more general problems with risk, we need dynamic optimization, which can sort of take care of this in a specific way. But that's for another video. Thank you for today.